Okay, we are recording. Double check. Yep. Okay, we are recording. Thank you for reminding me. Okay, I'm going to honor the promise to keep this course math light, so we're not going to be doing any calculations, such as they do in this section I've cited here, carboxylic acids at physiological pH and all that. If you don't know how to do some of these basic calculations in your chemistry major, you better fix it. You know, you learned a lot of quantitative things in Gen Chem. You're going to need that in the future. Okay, so on the top here is what I would consider carboxylic acids and their derivatives in the broadest sense. It's a carbonyl group with two things attached, neither one is a hydrogen or carbon. Okay, or no, at least one of them is not a hydrogen carbon. I'm sorry, misspoke. At least one of them is not hydrogen or carbon, and the other one is about anything. Here are the ones where it's carbon. So we got carboxylic acids, acid chlorides, esters, amides, and nitriles, and you should all be familiar with these. And the carbon of the carbonyl group is at the same oxidation state in all of them. That's why they're so related. Okay, carboxylic acid has been known forever. The ancient Egyptians purified vinegar. Okay, and one reason they've been known, even in more modern times, 1800s and such, is they're easy to isolate because they dissolve in base. Okay, they're soluble in sodium hydroxide, and so are phenols, if you remember. But they're also soluble in bicarbonate, which differentiates them from phenols. Okay, because they've been known so long, there's lots and lots and lots of common names. The compound has a common name. It's been known for a long time. Yeah, making soap is hydrolyzing fatty esters. I can dig up some slides from my other class if we have time. You'll notice that the longer carboxylic acids almost always have an even number, because that's the way the biochemical machinery builds them. Fatty acids are made up of acetic acid units, so 2 carbons added at a time. The common ones have even numbers. When they're volatile, they tend to stink. Okay, now vinegar, you know, whether it stinks or not depends on how much you get, but some of them are a lot worse than vinegar in the way they smell. And they most commonly occur in nature as esters, as the essence of fruity or flowery smells. And they're commonly used in the perfume industry that way, but you don't want esters in your perfume. They tend to hydrolyze on your skin, and then they smell like carboxylic acid. So cheap perfume has esters, expensive perfume doesn't. These are the common names, and I love the origin of these names, so I'm going to go through it, but not in bold, so I won't test on it. The simplest one, formic acid, with a hydrogen instead of a carbon on one side. The formic part of the name comes from formica, which is Latin for ant. If you've ever had an ant sting you and it burned, that ant just injected formic acid under your skin. Yeah, nasty little ant, although you were doing something to upset him. Acetic acid comes from the Latin for sour wine, which is exactly where vinegar comes from. Propionic acid, I don't know why it comes from the Greek for first fat. So I don't know where that comes from, but propionic acid occurs in sweat and in cheese. Now, sometimes a tiny bit of something that has a bad odor makes something smell characteristic, and we have a positive association with that. So a tiny bit of something can be good, and more can be really stinky. Just had a little doggy join me. Butyric acid is probably the worst smelling one of this bunch. It comes from the Latin word for butter, because it's known, just a minute, Meg is in her little bed next to me on the chair. See, I'm standing. Fluent, rancid butter. And it also is present in vomit and gives vomit its wonderful smell. Okay. Okay, going on, they get less volatile. So valeric acid doesn't have a whole lot of odor. It's now less volatile and less odor. And it comes from the valerian plant. If you know what that is, maybe you can tell me. And those are the 5 that I usually require students to memorize, of course, for open book, but they're worth knowing, especially the first 4. Valeric acid is not used as commonly, but from butyric on up, the first 4 are used widely. So you might want to know them fairly well. If anybody has the sign of Capricorn, there are 3 acids named in your honor, I guess. They all come from Latin, the goat. There's caprylic, caprylic, and capric acid. When I was a student in this course, I had to figure out how to remember which one is which. I had to learn through 10. You only have to learn through 5. And notice we've switched to even numbers. Lauric acid is 12. It comes from the laurel plant. Myristic acid comes from nutmeg. You know, that toxic stuff that tastes so good. I love fresh nutmeg on my, well, eggnog and other things. But I don't know if you realize it. You eat too much eggnog, you'll get sick. It's toxic. Oh, the cats like the valerian plant? Okay. Palmitic acid, yeah, palm oil. And stearic acid, I've emphasized, it's the essence of beef fat. It's the most common fatty acid in the triglycerides that are tallow, beef, which is where the name comes from. Okay, so stearic acid's important enough, you probably should know that one too. Okay, so those are the common names. Nicholas, when I order a good steak at a good restaurant, I tell them if the middle's warm, I'm sending it back. Okay, and here, frogs are polite, being very courteous. Helps you remember F-A-P-B, whatever, V. And the C you can ignore unless you're a Capricorn, and then you'll think it's cool. My twin brother used to tell the waitress, knock off the horns and hooves and pass it over a match twice. When you take biochem, you will have to do calculations, I promise you. Okay, the Greek alphabet, again, this is where it really comes from, is the carboxylic acids, I believe, the original thing. And so instead of the 1, 2, 3, 4 I'm showing here is alpha, beta, gamma. We introduced that with aldehydes, but it originates with the carboxylic acids. And, you know, I think the rest is clear. So this is gamma hydroxybutyric acid, or GABA. And this is IUPAC 4-hydroxybutanoic acid. Please don't mix and match them. We would never use 4 with butyric acid or gamma with butanoic acid, okay? Stay in common names or stay in IUPAC names. Okay, and gamma is used in other settings, like this is gamma butyrolactone. It's the lactone of gamma hydroxybutyric acid, but that's the name most commonly used for this compound. And a lactone, I think I mentioned this before, is a cyclic ester, and a lactam is a cyclic amide. You may know what beta-lactams are, penicillin and the like. So that's where the lactam comes from. Okay, carboxylic acid nomenclature is nothing really new, just a variation. So ethane becomes ethanoic acid, the formal name for vinegar or distilled vinegar. And again, just like aldehydes, you don't need a number. Carboxylic acid has to be 1. So here's a couple of possibilities. 3-methoxypentanoic acid would be the IUPAC name for this. Beta-methoxyvaleric acid, why there's an S there, I don't know. Beta-methoxyvaleric acid would be the common name for that. Okay, Okay, so here's just some more random examples. So I'm using the oxo here to help you get used to it. Carboxylic acid takes priority over aldehydes. So the acid would get number one. Good question, Pooja. So this is 4-methyl, 5-oxo-hexanoic acid. And notice it is alphabetical. Oxo has no particular priority here. It's just a substituent. We introduced oxo in the last chapter. Oxo means put a ketone there. Or it could be an aldehyde. Okay, oxo means put a carbonyl group on the 5th carbon. Okay, here is 4-phenylbutanoic acid or gamma-phenylbutyric acid. And here's an important one, 2-hydroxypropanoic acid, alpha-hydroxy propionic acid, or hey, lactic acid. Now, lactic acid is probably the name you want to remember long term, but I'm not going to worry about it. Ephraim, you have a question?
Yes, I have a question for the naming part of the homework. For some reason, the answers that were given seemed to be the common name. Like, for example, when the common name wasn't specified to give, like I gave, for example, NN-dimethyl methanamide, but the answer key showed that it was NN-dimethyl
Okay, well, my
formamide.
answer
Why
keys
why
are
was the common?
my answer keys are never intended to be comprehensive. If your name is right, it's right. I don't remember the instructions. It didn't say common name, it just said name it.
Yeah, it didn't say common
Yeah,
name.
I probably should have both names on the answer key.
Okay, all right. So
But don't let that bother you.
All right, thank you.
You know, I probably put the common names there because that's what takes getting some used to now. Okay, thanks for asking.
No problem. Thank you.
And I put your hand down. Okay, diacids are also important. Dicarboxylic acids, where one's on either end of the main chain. 2 carbons, that's no carbons in between the carbonyls, is oxalic acid. It comes from the sorrel plant, the name, if you're interested in the etymology. I love the etymology of language. Just wish I knew where Hammond came from. So anyway, but it's also known in rhubarb leaves. In fact, you can't eat rhubarb leaves. They have enough oxalic acid to be toxic. Oxalic acid complex with iron and other metals, and that's not good if you have too much of it. So if you like rhubarb stems, go right at it. Rhubarb strawberry pie is a classic. I don't like it. You can have mine. Malonic acid was originally identified in apples, but a common source is beets. Succinic acid is particularly important in organic chemistry. It's found in beer and especially wine, but it's also quite prevalent as a constituent of amber. I taught as a visiting professor at Vassar College for a year. They have an amber lab. You give them a piece of amber, they'll tell you where it came from. You know, they analyze it. And succinic acid derivatives are very common in there. Glutaric acid, you have a little bit in your urine, and it's isolated from gluten. Adipic acid is a product of fat oxidation that comes from the Latin for animal fat, okay? And then pimelic, fubaric, azelaic, sebaceous. I mean, the names go on and on and on. But knowing through 6 is also important, adipic acid, because nylon 66, one of the original and most common nylons now, has that as one of the constituents. Okay, just a minute. Yeah, if you like rhubarb pie, yeah, that's your business. If you've never had the pleasure and you have a chance to bite into a raw rhubarb stem, be my guest, but I warned you. It is very, it's about as sour as things come. And here's, oh my God, such good apples to help you remember the first 5. Okay. And here are some other important ones. Maleic acid, we know from Diels-Alder reactions. Maleic anhydride and maleimide were used. The trans is also known, but we won't worry about that. And then there's the 3 isomers, the dicarboxylic acid, the benzoic acid. The one that's most important is phthalic acid. So I'd like you to learn that one. Isophthalic is kind of easy, one more. And terphthalic acid, I should emphasize, because it's part of the PET, soda bottle plastic. Polyethylene terphthalate. We'll see that later. Okay, IUPAC names are nothing new. Got diols, diones, dioic acids. Okay, so this one, the bottom name, 2,2,3-trimethyl butane dioic acid, more commonly called 2,2,3-dimethyl succinic acid. And down here, I just got a little fancy, 2,2-difluoro 4-hydroxy pentane dioic acid. And part of the point here is that the alcohol has no priority over the fluorine. There's 2 fluorines, they win, they get 2. Okay, again, once you've established your main function group, everything else just becomes a substituent in one pool. Okay? Esters, I'm going to go through all the nomenclature first. Esters, when they were first made, they weren't sure the nature of them, and their name has the same. The acids have to be 2 ends of the chain. That's it. A hexane dioic acid is a 6-carbon chain with an acid on each end, always. There's no other choice. Okay. So esters have the names resembling salts, because when they first identified them, they didn't know the difference between ionic and covalent compounds. So ethyl is the radical name here, the ethyl that used as a substituent, the substituent name, ethyl, and then acetate, like sodium acetate. Okay, and we see this in ethyl chloride, which has the same form as sodium chloride. So these names remind us of an era when they didn't know the difference, but the pattern of the names has continued. Ethyl chloride is not the IUPAC name, it's chloroethane, but this is how esters are still named. So ethyl acetate is in fingernail polish remover if you don't like acetone. Okay? But you guys know the difference. Ethyl acetate's easy to distill, sodium acetate, not so much. Ethyl acetate's not miscible with water. Sodium acetate is very soluble at higher temperature. Anyway, so when you name an ester, you have to distinguish the 2 parts. I've done that for you here in color. First, look at the blue and name the acid. So this would be 1,2,3-methyl butaneoic acid. Change it to butanoate, the salt form, just like you had sodium 3-methyl butanoate. Okay, so that's the ending of the name. And now look over here, methyl. I will keep the alcohol side of the ester relatively simple because you have to name it as a substituent. I don't want to get it too complicated. I may cross the line, but only in your mind. Okay, this is also methyl, beta methyl butyrate. So butyric acid becomes butyrate. Okay, and this is a 5-carbon acid and is also known as isovalerate. There's isobutyrate too. So the iso means 2 methyls at the end of the chain. So that's just an extension of like isopentyl. Isovaleric acid. Okay, iso always means this in whatever context it's in. Okay. Oh, I didn't emphasize here. Let me emphasize. These are always spaced. It has 2 carbon chains, right? Separated by an oxygen. So there's inherently a space in the name of esters, but not ethers. So here's just some more examples. Ethyl paramethyl benzoate. So again, the acid here is paramethyl benzoic acid. Ethyl paramethyl benzoate. And my PowerPoint is having a problem. It's auto recovering. I don't know why it does that. Here's something a little fancier. So the alcohol side is sec-butyl as a substituent. Okay, there is an IUPAC form of this, but I'm not going to worry about it. It's actually 1-methylpropyl, but then 4-chlorobutanoate. So a little bit, a little more complicated, hardly real complicated. Here's something, this is probably the most challenging I'd ask you to name on an exam. And here you would go to IUPAC. So what is the radical here? Well, it's a phenyl group with a 3-methoxy. You don't name ethyl esters on the left here as ethanol, you have ethyl. You don't name esters of phenol based on the name phenol, you base them on the name of phenyl. So this is 3-methoxyphenyl, and now we have 3-methyl pentanoate, okay? So if you didn't follow clearly, spend some time with these. Esters have 2-part names, and it's not that hard once you see it. Okay. Amide nomenclature. So butyric acid becomes butyramide. Butanoic acid becomes butanamide. So common and IUPAC name. Okay. So here is N-phenyl benzamide. So N is used just like amines. Okay, so this is a primary amide. For secondary amide, you need the N-phenyl. And benzamide from benzoic acid. And here is a good example. Here on the left is isobutyric acid. So this is N,N-dimethyl isobutyramide. Okay, just using that iso. But the IUPAC name is NN2 trimethyl propanamide. And this may be the same first time you've seen this, where the N and the 2 all come together. Maybe it's back in the amines, but they get clustered. The N's are treated just like numbers. Okay, so NN2 trimethyl propanamide. Okay, I hope you're following. Nitriles, butyric acid, butyronitriol. Let me back up again. The N means the phenyl groups on the nitrogen. And please don't write a small case. I'm seeing it on the exam and it looks so bad. Capital N, it's a nitrogen. Elements get capitals. NN, the N has to be repeated just like a number has to be repeated, because there are 2 methyls on the nitrogen and you need an N for each one. 3 methyls, where are they? One's on nitrogen, another's on nitrogen, and one's on the 2-carbon. Okay, so you always need the right number of locants, is what that's called. Nitrile, I don't know exactly what the polymer is for nitrile gloves, but they're very resistant to chemicals and they're not allergic. I greatly prefer latex, thank you. So butyronitriol, butanitrile. This is benzonitrile. This is isobutyronitriol would be the most common name for that, or 2-methylpropane nitrile. Again, for carboxylic acids are the derivatives. Simple compounds generally use the common names in common usage. Okay, acid chlorides, butyric acid, butyryl chloride. Now it's 2 words again. Butanoic acid, butanoyl chloride. So you guys got to get some of these patterns down. Okay, again, this isn't a complicated chapter, but it has a lot in it. Okay, so here's benzoyl chloride. So now you got to distinguish benzyl from benzoyl. Okay, one has a carbonyl group. This is isobutyryl chloride or 2-methylpropanoyl chloride. So I'm following many of the same examples here with different compounds. Okay, these are all related compounds. They're all carboxylic acid derivatives. So I've done it that way. Anhydrides, when they're symmetrical, it's easy. So this is acetic, the anhydride of acetic acid, it's acetic anhydride. This is butyric acid, butyric anhydride. Butanoic acid, butanoic anhydride. So that's an easy one to learn. Okay. I don't have the unsymmetrical anhydrides here. I have to see, maybe that's later. But then you need to designate both parts. Okay, I want to talk a little bit about the polarity of carboxylic acids, although it's not the most important property of carboxylic acids, okay? The oxygen in the lowest energy conformation is sp squared, and there's resonance with the carbonyl group. Okay, I hope you all can see that now. I hope you're all good enough with resonance. I don't have to draw everything out in detail, okay? And because that is sp squared, this hydrogen is planar with the oxygen, carbon. So all the atoms explicitly designated are planar in the lowest energy conformation, meaning they're two isomers. Now, these things cannot be isolated. I don't think you can even resolve them at very low temperatures, okay? They're in ready equilibrium, but they do exist. And it's the one on the right that is the lower energy, okay? So on average, it's there more often. Okay, so the carbonyl has a very strong dipole, ketones, aldehydes, pi bonds, polarizability. Okay, and the oxygen here has a lone pair going down that constitute another dipole, and the bond dipoles here add to that to some extent. Okay, so carboxylic acids have two dipoles in the low energy conformation. They oppose each other. Okay, and so here is the electron density map, and you can see the bright red charge here for the oxygen of the carbonyl group, and a lighter red area here for the oxygen of the OH. Okay, so you have these two concentrations of negative charge, and the little bottom one cancels some of the carbonyl polarity. Okay, now you also have the H here, and that's the important part of a carboxylic acid. But the dipole in a carboxylic acid is weaker than the dipole in aldehydes and ketones. Okay, so they are less polar than ketones, and it's hydrogen bonding that dominates. And I'm showing you here acetone to show you what it looks like. Okay, so this red and this red are comparable, but some of this is canceled on the top. Okay, now you've got to be very careful comparing these electron density maps. They have to be done from the same source using the same parameters. You can't just pick them at random from the internet and compare them. If they come from the same site, they probably have the same parameters. Okay, so bond polarity and molecular polarity are not the same thing. Okay, that should be clear. Okay, the OH bond is very polarized. Look at that blue out there. That blue is just waiting to hydrogen bond to, hey, an area that's red in a different molecule. Okay, the intermolecular interaction between carboxylic acid depends mostly on hydrogen bonding. Okay, but that doesn't mean that they have a larger dipole. Acetone has a larger molecular dipole than acetic acid, even though acetic acid has a much higher boiling point. Okay, so there's a difference between how strongly they interact, especially when hydrogen bonding is involved, and the molecular dipole. It's not the same thing. Molecular dipole is an average property for the whole molecule. But when you have hydrogen bonding, that's one site that's responsible for dramatic interaction. Okay, it's different. I hope that is clear. We'll see the results of that. So here's some numbers just to prove it. Acetone has a dipole of 2.9 debis. Acetic acid has a a piddly little dipole of 1.7 Debye. Acetone is much more polar than acetic acid. Compare with. CF is a short for a Latin phrase I can never remember. It means compare with acetone. Okay. Water and acetic acid have about the same molecular dipole. And just to look ahead a little bit, amides have huge dipoles. Okay. So esters and carboxylic acids have smaller dipoles than aldehydes and ketones. And we'll see that amides have much larger. Okay. Try to keep that straight if you can. You have to think of the properties that reflect the whole molecule and local properties that reflect specific interactions. They are not the same thing. Okay, so here is our latest list of boiling points. You knew this was coming. So butane, methoxyethane, because this is one of the two smallest ethers, there is a little difference here. But I wanted to compare them with acetic acid, so that's the size I picked. Acetone has a nice dipole, so it's higher. Isopropyl, hey, it's got good hydrogen bonding, it's even higher. And acetic acid is what? 35 degrees higher. Big jump. Okay, so from acetone to isopropanol, adding that hydrogen bond is 30 plus degrees. And improving the hydrogen bond by going to acetic acid adds almost as much, or actually a little more. Okay, so carboxylic acids have very strong hydrogen bonds, and that's responsible for very high boiling points, higher than alcohols by a lot. If you try to distill these two, you will notice the difference. Okay, now, everybody, pause for a second and listen to what I'm going to say, because this is wrong all over the internet and in textbooks. Why do carboxylic acids have so much higher boiling points? And you'll often see it explained that, oh, they make dimers, they distill as dimers. That's not an explanation. That begs the question why they make dimers. Why do they distill as dimers? They distill as dimers because they can do so and not give up two strong hydrogen bonds. It's the strong hydrogen bonds that lead them to form dimers. So the ultimate reason carboxylic acids have high boiling points is not that they distill as dimers. The ultimate reason is they make very strong hydrogen bonds. And it just so happens that the dimer has a lower boiling point than the monomer. We have to break two more hydrogen bonds. Okay, you got that clear? So they don't distill higher because they're dimers. They distill higher because of the strong hydrogen bonds. And in the air, they separate anyway. I mean, entropy always wins. At the end of the day, the whole universe is going to go dark. Entropy is going to win. That's a long way off. I don't know about diacids. They probably just depends on the size. They may make an intermolecular dimer at some point, or not dimer, but association. By the way, the dimers of carboxylic acids are longer persistent. They're a lot easier to study, but methanol also distills as a much less stable dimer. And if you want to get strange, the metal mercury, that silver liquid that's fun to play with, but don't do it, you're going to fry your brain. It's not that bad. I've played with it. Maybe that's what happened to me. Anyway, mercury distills as a dimer, Hg2. Yep, it's not that unusual to distill as a dimer. It all depends on what the forces are and what ends up with the lowest boiling point. So acetic acid distills as a dimer because it has a lower boiling point. It forms a dimer because of the strong hydrogen bonds. Have I whipped that dead horse long enough? All with apologies to all the horse lovers. Okay. It's the strong hydrogen bonds that's responsible for it. And in solution, they don't exist primarily as dimers. They exist, carboxylic acids exist, especially acetic acid, as a network of all sorts of hydrogen bonding. It's all random. It's not well organized into dimers in the liquid state. But when you heat it up, it's the dimer that says, oh, hey, I can leave. It has the lowest boiling point. But it's the strong hydrogen bonds that keep it in the liquid form up to that point, okay? Okay, so here's the math. You know what equilibrium constants are. Here they are. It's not going to be on exams, don't worry. But if you can't deal with this and you're a chemistry major, go back and review your Gen Chem when you get a chance. Yeah, I mean, they distill as dimers. A dimer would inherently have a higher boiling point, but it begs the question of why they form dimers. They form dimers because the strong hydrogen bonds. It doesn't want to give up all the hydrogen bonds. The underlying cause is the strong hydrogen bonds. Okay, so this is the formal calculation of an acid ionization constant. The pK is just like pH. And for acetic acid, it's 476. So you see a little variation in that last number. And just to feel a little feeling, if you've got 0.1 molar acetic acid, this equation can let you calculate that it's about 1% ionized. So most of the acetic acid is in the acid form in just pure water when it's dilute. As it gets more concentrated, that percent goes down. Okay. So let's talk again about the stability of anions. Isopropanol is not an acid in water, not to any significant extent. And the reason it's less stable is the oxygen is alone carrying the negative charge with whatever it can force into the sigma framework onto the carbons. Okay? And its stability in water depends also on how well it's solvated. So this is reviewing what we learned before about the acidity of alcohols in water. Okay, but it's just not really an acid in water. It's a terrible, terrible, terrible acid in water, virtually unionized. Okay, alcohols. I told you that there's two reasons that phenols. There's two reasons phenols are much more acidic than alcohols. It's in that range, yeah. Yeah, I'm trying to bring new attention to acids and bases. So one reason that phenol is more acidic is the negative charge on oxygen is stabilized by the fact that it's attached to an sp² carbon, a more electronegative carbon. That part of it is often skipped in the textbooks, okay? But the other part of it is resonance. And I don't know the relative importance of the two, but I do for carboxylic acids. Okay, so a carboxylic acid is more acidic for two reasons. First off, the oxygen anion is on not just an sp² carbon, but an sp² carbon with an electronegative oxygen on it. So this carbon has a slight positive charge. It's much more electronegative than the carbon above in phenol. Okay, so that is a stabilizing influence. And then resonance is in addition to that. So these are two separate factors, the same way they are with the phenoxide stability. Okay, and there was a publication on this when I was in graduate school. Everybody was passing it around, saying this is strange because we always thought it was resonance. It's about half and half. You know, there's no way to measure this in the lab. Based on high-end calculations, half and half. And the reason the carboxylic acids are so much better than phenols is first off, you have two oxygens helping, with the resonance structures in phenol are all on carbon, poor carbon. But also, this resonance costs you nothing. For the phenoxide, it costs you an aromatic ring. Okay, so we have pKs of about 16, about 10, and about 5. Big changes. Okay, so take this slide to heart. And yeah, the exam question too, that some people did very well on, but certainly not everybody. So here is the emphasis here. Calculations indicate that both the resonance and the increased electronegativity of neighboring carbons or neighboring atoms is responsible for the increased acidity of carboxylic acids. Sorry, I got my shirt twisted. Yeah, nobody said anything about my appearance today. Anybody do a double take? Yeah, my summer cut. And I got a button-down shirt on just for you guys. Well, for my wife too, it's Friday. Yeah, I'm gonna get a suntan really soon, and I don't want the first haircut I get after that to give me a ring of white. Yeah, I have a skin condition and sun's the treatment. So, hey, that's a medicine I can take. Okay, so again, resonance structures. The negative charge is not on one oxygen and then the other. And here is the electron density map. So here's the carboxylic acid I showed before with the large dipole and the small dipole giving a smaller molecular dipole than ketones. And here's the carboxylate. And this is the structure all of the time. Resonance structures don't exist. Here it's a 50-50 average because it's symmetrical, and the two oxygens are carrying equal charge all of the time, okay? And of course, notice how much more red there is here than in the carboxylic acid, because hey, you got a negative charge here. The colors average out on the left, they don't on the right. Okay, I wish I didn't have to go through this, and I wish I could go through it earlier in the year. I want to go through extractions. I've taught Chem 225, and it was disturbing to me how many students had done extractions before. Just a minute. They'd done extractions before by just following the instructions, and they didn't know what they were doing. So if you're not absolutely certain how extractions work, it's far too important to leave them there. So these are the slides I made for my other class to explain how extractions work. This should be solid knowledge you barely have to think about if you consider yourself good at organic chemistry, especially in the lab. This is day in and day out. Okay, so my example, the green box, we'll call it, is ether. And I've got 4 compounds dissolved in it. An alcohol, an amine, a carboxylic acid, and a phenol. Okay, yeah, if you haven't taken 225 yet, take this very seriously. It'll make 225 easier. So I've picked, of course, the 4 functional groups that we might consider. I've got a weak acid, a very weak acid, a weak base, and a neutral compound. They're all about the same size. I made them all aromatic. And the blue indicates a water phase, okay? So you put this in, you shake the whole thing up, and you're always gonna get traces in the water. If for no other reason, then you're gonna have a little bit of ether dispersed in the water and dissolved in the water. A little water dissolves in the ether, a little ether dissolves in the water. They set up an equilibrium as well, but the organics are gonna be 99.9% in the ether. Okay, just tiny, tiny, tiny traces in the water. Okay, so let's change that and let's put hydrochloric acid in there. 1 molar is the standard for these things. Okay, everything you use is 1 molar. So you put in water with HCl in it, and you shake the 2 phases together, the ether and the water get shaken. You're going to extract the amine into the water as the ammonium salt. The other 3 molecules just watch the action because they don't react with acids. So you got to know acid-base chemistry and you got to know solubility. So making the amine ionic changes its solubility from preferring ether to preferring water. That's what the charge does. Okay, ionic compounds are not very soluble in ether at all. Okay. Okay. So then you extract with bicarbonate and you pull out the carboxylic acid. You don't want to extract the carboxylic acid sodium hydroxide because you're going to get the phenol as well. You want one at a time to use the weaker base to get out the stronger acid first. Okay. And now you extract with sodium hydroxide and you get the phenol out as the phenoxide. All the compounds as they go into water are ionic, cations or anions. And now you have the ether left with the alcohol in it. Okay, now there are traces of the other compounds still in here, right? Tiny traces of nothing else. If you're good, you'll never see them. Having compounds in water as ionic compounds is very inconvenient for organic molecules. So we have to reverse the process. So to the amine, we've got an HCl. We're going to add excess sodium hydroxide. We're going to make salt. And the amine now wants to go back in the ether. Good. We've gotten rid of all the excess salts. And we've gotten our compound back out of water into ether, where we can handle it much more easily. Okay. We do the same thing with a carboxylic acid, but everybody note how careful you have to be. You throw in the acid, it's going to foam all over the bench top, and everybody's going to laugh at you, except the lab tech. He's going to tell you to clean it up. So you have to add the HCl very slowly because bicarbonate creates carbon dioxide, which comes bubbling out. So you go very slowly until it gets less energetic. Then you can go faster. At the end of the day, you make it acidic. You shake it up back into ether. Yeah, I'm not showing a SEP funnel. I assume you know what that is. And the sodium hydroxide you use to dissolve the phenol as a phenoxide, you neutralize as well with 1 molar HCl. And you want to be a little careful doing this because HCl and sodium hydroxide generates heat. And if you're working with concentration solution, you can get the heat ether hot enough, get a very significant vapor pressure. Okay, so venting separatory funnels is habit. Don't even think, vent, then vent again. And if you think you don't need to vent again anyway, okay? You can't vent too much. Making mistakes in the lab is how I learn. Be careful. There are mistakes that can cost you fingers or your life. So you want to make little mistakes, not big ones. So at the end of the day, you have the amine and ether, and you used HCl to get it out of the water initially. That's the ultimate source of this. Carboxylic acid was extracted with bicarbonate. Phenol was extracted with hydroxide. And the alcohol just watched all the fun and it stayed in the ether. Now, these ether solutions aren't that clean. They got traces of water in it. They'll have traces of salts in it. There'll be a little bit of particulate droplets of very small droplets of water in the ether. So you got to dry it. Sodium sulfate, magnesium sulfate are the two most common. Then you filter it. And then you use a rotary evaporator or whatever method you want to get rid of the ether. And you have your compounds. Final recrystallization, they're pure. Although I don't think the top one's crystalline. The others, I don't know if the bottom one is or not. These two would be crystalline. Okay. So that is how extractions work. I am now entitled to ask questions about this on the exam. Jack Riel, is that the name? The amine was protein dissolved. The carboxylic acid and the phenols were deprotonated to dissolve. They became ionic, acting as either a base or as acids. So you need a good understanding of acid-base behavior, and you need a good understanding of solubility behavior. I reserve the right to ask whatever question I want about extractions on the exam because I just did it. And it is the heart and soul of organic chemistry in the lab. Okay, so learn this for your own good. And if you've been struggling in this with Orgo 2 lab, you still got time to learn it. Okay, I want to make a comment about bicarbonates, risking going a little too far. So bicarbonate is the monosodium salt of carbonic acid, right? And so what is the pK of sodium hydrogen carbonate, to give it a formal name, sodium bicarbonate. Well, its formal pKa is 3.6. The pKa means the conjugate acid, okay? So we're really talking about the pK of carbonic acid. So the formal pK of carbonic acid is 3.6. It's a much stronger acid than carboxylic acids, and it should be, as our discussion is going to indicate, okay? But we never use that number in the real world. We use the apparent pKa of 6.4, meaning it's a weaker acid than carboxylic acids, which is why it doesn't extract them. Okay, so what's the rub here? Why are there two different pKa's for the same thing? Well, in the formal sense, this equilibrium determines the pKa's. But that equilibrium has a problem. This carbonic acid has another reaction it can do. This carbonic acid will decompose to carbon dioxide and water, and the carbon dioxide is free to escape. Okay, so according to Le Chatelier, the bicarbonate will react more than we expect it to do the deprotonation, okay? So bicarbonate should not deprotonate carboxylic acids. The pKa is all wrong. It's a factor of 10 off. But it works very well because the loss of carbon dioxide drives the deprotonation, okay? So the top equation indicate, 5–10% of the carboxylate. The bottom one would say, it's going to be more like 97%, if you look at the numbers, okay? And generally when you extract with bicarbonate, you'll do it twice to make sure you get pretty much everything, okay? So bicarbonate is formally not strong enough to deprotonate a carboxylic acid, but we do this in open separatory funnels. The carbon dioxide escapes and it drives the equilibrium. So we can deprotonate it pretty much to completion. Okay, and note this equilibrium was also driven because the carboxylate goes into the water. So that's still another factor. It's not in a single equilibrium. You've got the distribution of things between the two phases as well. Okay? Okay, so let's talk about acid strength now in a more general sense. So formic acid is stronger than acetic acid. Generally, they teach that that is because the methyl group is a electron donating group, right, compared to hydrogen, and therefore acetic acid less acidic. I don't buy that. Okay, it's more likely due to the better solvation of the formate anion, the same way alkoxides work. Le Chatelier's principle drives the formation of carbonic acid because that carbonic acid is then decomposed to carbon dioxide. It makes the bicarbonate more reactive, in a sense. Jackie.
I'm just confused about why the pKa's are different. Is it because of the loss of CO2 that there's a higher?
The formal pK at the top relies on starting out with 1 atmosphere of carbon dioxide.
Okay.
So that is in there suppressing the decomposition.
Okay, and then if you have a lower vapor, if you have a lower pressure of CO2,
we let the carbon dioxide escape.
Right. So if you let it escape, then the pKa goes up.
The apparent pKa.
Okay.
The formal pKa is always 3.6. But who cares? Everybody, you look this up all over the place. They just give the pK of 6.4. But from what I'm going to talk about with dicarboxylic acid, that doesn't make sense. which is why I'm doing this.
Thank you.
Yeah. Yeah, the pKa acts like it's much higher because of the loss of carbon dioxide. Okay. Okay. So formic acid is a stronger acid because it's better solvated. I don't know if that's in the literature, but I'm convinced of it. There's another acid, I'm not asking you to learn the name, but it has some significance in organic chemistry. It's pivelic acid, not much difference. So putting a T-butyl group here is too far away from the anion to affect solubilization in water. Adipic acid and oxalic acid are two dicarboxylic acids, and I want to spend some time talking about their pKa's. Notice that adipic acid has two pKa's that are close together. Oxalic acid has two pKa's that are quite a bit more acidic. So we've got to understand this, okay? I don't know if I have another slide. Okay, oxalic acid, if you make the anion here, you've got the resonance, but you've got a lot of other electronegative atoms in the vicinity, and that increases its acidity. But even the second one is more acidic, and I am less apt to explain that. That may have to do with solvation too. I've never seen an explanation for that. Let's look at adipic acid, because oxalic acid has both factors. Adipic acid acts like two carboxylic acids because they're so far apart, they don't influence each other. So why are there two values? It's an artifact of how we look at it. Per carboxylic acid group, it's not really different. But if you put this in there, make a 1 molar solution, you've made 2 molar acid. So our 1 molar solution of adipic acid has a pKa that's shifted to more acidic because there's actually more acid in there than the formal concentration indicates, okay? And the second ionization is higher because it's just less likely to have both of them ionized at once on the same molecule, because ionization is a minor process here in water, okay? Is that a new hand raise, Jackie, or an old one?
It's a new one.
Okay.
Will that self-hydrogen bond and make like a pseudo ring?
This, I doubt it. It's a kind of a big ring. But I like the way you're thinking. So the adipic acid, the fact that it has two pKa's is really statistical in nature. Okay. And you can actually use statistics to take a normal pK of acetic acid and calculate these two values. No, I'm not going to ask you to do that on the exam. Okay, so all carboxylic acids, all dicarboxylic acids have 2 pKa's, tricarboxylic acids have 3 pKa's, and sometimes they're close together and they influence each other. If they don't and they're far apart, the difference in the pKa's is statistical in nature. If there's 2 of them in one molecule, it's just much more likely that one of them or the other is going to ionize. But it's also less likely that both of them will ionize. And so you get the 2 values split from the normal value. 4.8 is roughly in the middle here. So it just shifts both ways. Okay. Oxalic acid has that as well, but it has all this dense oxygen here, making that first one much more acidic. This carbon of the other carboxylic acids unionized is pretty electronegative. It's sp squared and it's got 2 oxygens on it. So it really helps stabilize the anion on the right. Okay, so 1.3 is an impressive carboxylic acid. And the 4.1 is the odds of both of them being ionized. Again, I can't explain why it's more acidic than acetic acid other than to suggest it's better solvated. I've never actually seen an explanation. Okay, benzoic acid is a slightly stronger carboxylic acid. Can you make sense out of that? The carbon next to the carbonyl group is sp squared. It's a small influence, but a predictable one, or at least one you should be able to explain. Okay, if you put chlorines close by, of course, it gets more acidic. Chloroacetic acid, dichloroacetic acid, trichloroacetic acid, and trifluoroacetic acid make a nice range of acid catalysts from weaker to stronger. Okay, sometimes changing from one to the other leads to a better reaction. By the time you get to trifluoroacetic acid, it's doing a very good job of trying to be a strong acid. Okay, so it's a range here. Each chlorine just keeps on making it more acidic because of the inductive effect of the electronegative chlorines that are nearby. Okay, and fluorine isn't that big a difference from chlorine, but 0.5 is a real difference. Trifluoroacetic acid has special importance in HPLC, high pressure liquid chromatography. It's a very common additive to the solvents. It's also used very commonly as a reagent. Giselle.
So on an exam, like if we were ranking acids, how would you rank benzoic acid and adipic acid? Like how would you
I
make a
probably wouldn't
decision?
mix and match that way. I'll try to be nice.
So it would only be like one
If I'm going to look at
carboxylic acid?
dicarboxylic acids, I'll look at dicarboxylic acids. Single
Okay.
variables.
Okay, thank you.
Maybe in a dream some night I have this evil idea and I put it on the exam. I don't promise, but in general, I will keep the questions a little more straightforward comparisons. Okay, and here's some touch points from Gen Chem. Phosphoric acid is not a strong acid. Oh, 5-minute break. Yes, please, I could use it after this slide. Okay, nitric acid is a borderline strong acid. Everybody considers it a strong acid, but it's not that impressive. -1 is where I kind of draw the line. HCl is -6, sulfuric acid is -3. Hydronium ion can be assigned a pK of -1.7. For some people, that would be the borderline between strong and weak acids. Okay, so these are just touch points. Anybody who considers themselves a real chemist should have some feeling for this. Okay, and by the way, if you look in the literature for the pK of sulfuric acid or HCl, you see lots of different numbers because it can't be measured directly. Different ways of estimating it does give different numbers. Okay, so here's more of an explanation. We'll do that after break. It's already getting a little late. Okay, so take 5, everybody. How many lectures for this? Let me look. I think 2 are scheduled. It may go over a little bit into a third if it has to, because the next one has 3, but I have 2 scheduled for this. Oh, quit your complaining. Yeah, I don't want to feel too ignored. I woke her up from a good nap. What? You can say hi. She doesn't know you guys are there. Take a walk after this. Yeah, I just woke her up. I took a relatively short walk this morning. It was too cold. At least for April. Omega dislike. Oh, there we go. Watch it. My dog hates other dogs. Anybody else with a dog? Mine's a little more travel sized.
Leo's only 15 pounds.
Oh, really? Looks
Yeah.
bigger. That must be a lot of hair there.
Yeah, he if you took calipers to him, he'd lose like 3 inches.
Yeah.
See?
Yeah, well, this one's 12 pounds, so that's not a big difference.
No.
We used to have a dog that was half German Shepherd, half Keeshond. Keeshond is a European breed, more common over there. They have a thick double coat.
Oh,
And, you know, she was so miserable in the summer, the first couple years we had her. We started shaving her early in the summer, and she looked silly, but she was so much happier.
he got shaved in the summer because he was a little matted. I didn't know how matted he would get. And he looked a little bit sickly.
You don't brush him every day?
I mean, I do. He hates it. So but it's also once it gets to be 4 inches on either side, it's gonna get matted. So
Yeah, you got to take him to the barber now and then.
yeah, he gets it every 3 months now.
Yeah. Yeah, my mother used to have, she loves Siamese cats, pointed silvers, all that. And they get such terrible mats if you don't brush them out.
Yeah,
And then she'd have to take the scissors and cut it out. And you know what the cat thinks about that.
doesn't like it.
You might check for what I just bought, although your dog has quite different fur. I mean, this is the short of the short, yours is long.
Yeah,
You could probably braid it, at least on the
Oh.
ears.
not right now.
Yeah,
But at some
well,
point it
anyway,
comes.
what I bought was a glove. That has
Oh,
a
those.
rubber pad with knobs on one side. And Omega likes it so much more.
Because it's like a massage.
Yeah, kind of. Yeah. I got her a regular dog brush and she growled at me and sneered and threatened to bite me. She hated it.
That's kind of how this goes when we.
She liked the glove. So try the glove if you get a chance to buy one.
Yeah, I'll do that.
Yeah, any good pet store should have them.
Yeah, he's just due for a grooming soon, I think. But
Well, that's the nice thing about a short hair. You never have to groom them.
yeah, that's true. Oh,
Just
Leo-
shedding season, you have to brush them.
He's done.
Yeah, I'm going to put this one down too. Yeah, so I owe her a longer walk this afternoon as soon as we're done. Okay, we ready to go again, I hope? Okay, so again, I've kind of spoken through this, but here's is on a slide. So half molar adipic acid behaves like 1 molar acetic acid. That's really the difference, okay? And so it artificially, in my mind, has a lower pKa, simply because the acid concentration is just higher. So it's kind of a strange situation, but having both ends ionized at the same time is less likely statistically. And so the second pKa is larger. So again, the pK from acetic acid splits into 2 values roughly equal side of it. Okay, so you know, if this doesn't make intuitive sense for you, that's not a problem. Just remember they have 2 pKa's that are split, you know, roughly what is it? Roughly half a pK, roughly 1 pK from each other, or half a pK from the middle. Okay, oxalic acid, this anion, I forgot I had these slides that have the details. This anion is greatly stabilized by all the electronegativity on the left side. Okay, I said that already, so here it's on a slide. Yeah, and the second pK is better than I would expect for sure, but it's better solvated. Notice you're getting 2 negative charges fairly close to each other. Okay, and it may be that it chelates a cation, which helps. So I keep intending to look that up and see if there's anything in the literature on that, but I'm assuming it has to do with more unusual properties. Okay. Okay, what I said about carboxylic acid and their dipole. Oh, a theory you had a compound with a. Yeah, the more you put on, the more acidic it formally becomes. You might want to look up, Michael, tannic acids. They're a polyphenol in coffee and tea and especially red wine. If you like, some people don't like much tannin in their wine, and some people don't mind a fair amount of tannins in their wine. But they're polyphenols. And they can be hard on your stomach because of their increased acidity. I don't know of any large polycarboxylic acids. You know, they're really multiple. Well, it's proteins, but that's different. Okay, so for carboxylic acids, I hope I convinced you they don't have as good a dipole as ketones, but they have higher boiling points because of hydrogen bonding. Esters, now the dipole becomes important. Okay, so there is no hydrogen bonding in an ester. There's no OH group anymore. And it's just the dipole, it's weaker than a ketone. So guess where the boiling point comes? Okay, so line it up now. Alkanes and ethers. Esters come next, and then ketones, and then alcohols. Okay, so they come in between here with the carboxylic acids on the top. Okay, so they have a significant dipole. They have a pi bond with a carbonyl group, but it's not as good as a ketone. Jackie.
Where do the amines come in?
Well, you don't want to know, but I think that's on the next one. They are less than ketones because of what's on this slide, Rose. You have the large bond dipole that's similar to an aldehyde or ketone, and a smaller dipole that opposes it due to the other oxygen. Okay? If you remember, there were 2 red areas on the carboxylic acid. It's the same thing here. I think I repeat that at some point. No, I don't. So it has to do with opposing dipoles and the carbonyl group being part of the polarity of the carbonyl group being canceled a little bit. Okay. So here there's 18 degrees difference. And here there is, what is that, 24 degrees difference. So roughly in the middle. Okay. So we've learned that not all hydrogen bonds are equal. We've learned that not all dipoles are equal. Some are wimpy, like ethers. And we've learned that not all carbonyls, functional groups, have the same dipole. Okay. Water solubility, yeah. Been there, done that. Kind of boring. And again, there's a lot more variable here. So these are just fluctuations in solubility. So, as I said, solubility is a lot more boring. Once you realize all you need is hydrogen bonding, you don't need an OH or an NH to get water solubility. Okay, amides, I just want to emphasize their importance as solvents. Okay, dimethylformamide is a universal dipolar aprotic solvent, the term. There we go. Okay, so it's higher boiling, so it can be a nuisance because of the boiling point, but it's very useful, and it's not nearly as high boiling as DMSO. So DMF is an essential solvent in organic chemistry. The hydrogen here from the formic acid this is a formamide, right? A hydrogen here makes it a little bit more chemically sensitive. So sometimes you switch to DMA, N-dimethyl acetamide. Okay, it's even higher boiling, so yeah, you got to get rid of it someplace, but it's also more stable. Formic acid derivatives have some inherent instability. Other dipolar aprotic solvents, just to review, acetone. Right? I don't know if you guys remember the Finkelstein reaction, reacting alkyl chloride with sodium iodide in acetone. Okay, and the grandfather of all dipolar aprotic solvents is hexamethyl phosphoramide, HMPA. With this structure, it's a triamide of phosphoric acid. However, it's a mild carcinogen, very mild, but still, you got to respect it for that. So it's avoided, but when it's useful, nothing else takes its place. It has some very unique uses. It loves to associate with lithium cations, so it's used for that purpose. Okay, amides have resonance structures, okay? This nitrogen of an amide, when it's in its lowest energy conformation, is sp squared. So there's not free bond rotation. We talked about this in NMR, remember? So this is review. So you have these two conformations, and you can see them on NMR in most cases, not always. Each one has its own resonance structure, and the resonance structures have a double bond between the carbonyl carbon and the nitrogen when it's more of an iminium bond. Okay, so this hinders the free rotation. This bond between the carbonyl group and the nitrogen has some double bond character. How much depends on the amide, and it depends on the conditions, but it can be as high as, wait for it, 50% double bond character. That's a lot, just why you can see these in NMR. Okay, so amides have very, very large dipoles, impressive dipoles. I showed you the dipole moment for one before, okay? And, you know, this is to be compared with cis and trans alkenes. At low temperatures, these can be frozen out completely. And not that low for some of them, okay? Okay, now one obvious mind game here is what happens when they equilibrate and this bond does rotate. That happens readily at room temperature for most amides. Well, when it rotates, there's no resonance. There's no reason that nitrogen can't be sp cubed for a while. So when it starts to rotate, it says, why am I spending my time being sp squared? I'm not doing anything. So it goes sp cubed. Goes flat again, it goes sp squared. It's all in flux. It's all dynamic, okay? But we almost always talk about the low energy conformations, which are what's on the slide, okay? Okay, boiling point of amides, don't even try to distill them. They're scary high, okay? So this amide is 216 degrees and also always Celsius. That's hot. The secondary amide, this is primary, secondary amide is only a little bit lower. So these both have huge dipoles and hydrogen bonding. Okay, and the hydrogen bonding is more alcohol-like or better, depending on details. Okay, and here is the amide, 170. This amide that cannot hydrogen bond is higher boiling than a somewhat comparable carboxylic acid. Okay, so here's a dipole-dipole interaction that's stronger than the hydrogen bonding in carboxylic acids. Got it? Okay, so I just hopefully impressed you by how strong the hydrogen bonds are in carboxylic acids, right? We did that, you know, half an hour ago, whatever. But if you take an amide that's tertiary that cannot hydrogen bond, it's going to have a comparable or higher boiling point because the dipoles are huge. Okay, think of amides as being half ionic. So now you're comparing bonds that are half ionic with bonds that are simply hydrogen bonds. So that's one way to come to terms with it. Okay, there's a lot of ionic character in amides because the dipoles are that big. Now, it depends on the structure, depends on where they are. Yeah, there's a solvent, the environment around them. It's not one constant number, but these boiling points are huge because the dipoles are huge. If you add hydrogen bonding to that, it only goes up more. Okay? Giselle.
So for amines, the main driving force is hydrogen bonds, but for amides, it's dipoles.
Right. But if you look, adding a hydrogen bond takes it up 34 degrees. So, when I say give me the main interaction, amides is the one where I'd list two.
Okay.
Unless it's tertiary. Because those hydrogen bonds are significant and the dipoles are significant. Both are showing up here in this data. Okay. And as a result of this, the vast majority of primary and secondary amides are solids to begin with at room temperature. So these two compounds presumably are solids, although I didn't check these two. But there are not that many liquid amides around. They tend to be solids. Solubility in water. So how does this huge dipole impact it? It doesn't. Okay? So boiling point and solubility have to be thought of quite differently. I hope I've proven that to you by now. So amides hydrogen bond with water, hey, they can be soluble too. No big deal. They're comparable to carboxylic acids, same size and shape. So the water solubility gets a little boring after a while, especially seeing it's harder to predict to begin with. Okay. Just a warning, crystallinity creates real problems predicting solubility because you have the crystallinity has a certain crystal lattice strength. How strongly are the crystals held together, and that is very hard to predict. And those forces have to be broken to make it a liquid before it can even dissolve. Okay, so it's much harder to predict solubility of solids. They have an additional factor. Okay. So here, the energy needed to melt the crystals must be offset by the heat entropy gained by dissolution. That's one way to think about it. And I'm just giving you one melting point. The 5-carbon carboxylic acid amide, valiramide, that's 1, 2, 3, 4. Oops, 1, 2, 3, 4, 5. This one, it has a melting point of 80 degrees. So not even a trivial melting point. It's getting up there. Okay, here is a chart that I found once on the internet and I loved it. I said, why didn't I think to make this myself? These are all straight chain compounds, no branching. I showed this once before in answer questions, and I have added some things to it and I've ignored some things on it. This is the original key up here that shows the color and symbol codes. Down out, this shows the molar mass. Okay, so as long as you've got just carbon, nitrogen, oxygen, it shows the number of heavy atoms, if you will, those atoms. And these are straight chain, and then the boiling point. So as you make them larger, the boiling point goes up. And all 4 of these have very similar curves, and they are alkanes, chloroalkanes, and the chlorine counts for its full mass, so that's an effect. Alkenes, which I don't really want to deal with that much, but they don't have stronger induced dipoles by and large. Okay, only subtle differences, if any. And what's the last one? Ethers. Okay, so the boiling points of ethers versus alkanes at low temperature, at small size, the ethers have higher boiling points. At large size, the ethers have lower boiling points. Okay, we're going to call it a tie everywhere. Okay, next come the esters in between. I've added that line. They didn't have that on there, so I've estimated it without actually plotting data. Next comes aldehydes and ketones and aromatics. So the aldehydes and ketones are shown here. I parenthetically said that aromatic compounds tend to fall on this line too. So for aromatic compounds, the London dispersion force is comparable to dipoles in ketones. Okay, then come the alcohols, then come the carboxylic acids and the tertiary amides, which are fairly similar. And then the primary and secondary amides are the record winner in the functional groups we'll look at. Okay, so this is what we've been talking about in terms of boiling point trends. This shows the size and the functional group. And of course, branching is another factor. We need a three-dimensional plot to show that. Okay, I hope that helps put everything together. We're running out of functional groups. This is the last chapter with new functional groups, sort of. Okay, so I want to step through all the different functional groups and the interactions, okay? Weak to strong. So this is putting everything together for the semester. Alkanes, we haven't talked about alkenes. They go here too, and ethers. London dispersion forces. They're all induced dipoles. They're all temporary dipoles. Pick your term. They all three mean the same thing. Ethers have dipoles that are totally insignificant. If they were significant, they'd be higher boiling. They add nothing. So the major interaction in all three of these is London dispersion forces. Okay. Esters and ketones and aldehydes have dipole-dipole interactions. The esters are lower boiling. This is from weak to strong going down. So the esters have weak interactions. The ketones and aldehydes have stronger interactions from the dipole-dipoles. And aromatics, benzene and the like, have strong London dispersion forces that are as strong as ketones and stronger than esters. This list you learned in Gen Chem is just a tendency and not even that good a one. These are all overlapping. Okay. Alcohols have hydrogen bonds. Oh, and I don't even have a means on here. I've got to keep this manageable. The means come around the esters. There's hydrogen bonds around number 2. Alcohols have hydrogen bonding. Carboxylic acids have much more significant hydrogen bonding. So far we have 2 different strengths of London dispersion forces and 3 different strengths if you include the means of hydrogen bonds. And then amides have very strong dipoles and can have hydrogen bonding too. And then if you're wondering what 0 is, 0 are perfluoroalkanes. It's an area worth knowing a little bit about because they're in the news. Perfluorooctanoic acid is in the news. It's been used industrially, and it's one of these eternal pollutants that we should never have let out in the environment. So perfluoroalkanes are the simplest ones that just, hexane with, 14 fluorines instead of hydrogens, no hydrogens, okay? And they have very, very low boiling points. They have boiling points 200 degrees less than alkanes of similar mass. Now the fluorine's bigger, so that's being accounted for here. But perfluoroalkanes are extremely volatile because fluorines have those electrons held so tightly, they make terrible London dispersion forces. So now we have different strengths of London dispersion forces. The ones the fluorines interact in, the ones hydrogens interact in, and the ones pi clouds, aromatic clouds interact in. So London dispersion forces all vary from very weak to pretty strong. Dipoles go from worth ignoring to amazingly strong, and hydrogen bonds go from weak to strong. And actually, we're talking about medium strength hydrogen bonds. There are very weak and very strong hydrogen bonds that are talked about at all. We're in the middle range of hydrogen bonding. Okay, so hopefully this helps you put everything together and understand these forces better. Giselle, is that a new hand raise?
Yeah, can you just explain with aromatics, what like what if it's aromatics with different functional groups?
Well,
Like
it
what kind
gets
of
complicated
aromatics
at some
do you
point.
mean?
I'm not going to get that complicated.
So you really just mean like alkyl aromatics?
Yeah, I'm
Like
talking
this
about
is
toluene,
okay.
benzene, xylene.
Okay, that makes sense. Thank you.
One of my favorite names is acetylene. That's 1,3,5-trimethylbenzene. It is an impurity in cheap acetone. I think I'm going to have that mentioned in the next chapter. Okay. So preparation of carboxylic acids, you know some already. You oxidize primary alcohols, right? Okay. Mechanisms for carboxylic acids and derivatives focus on the carbonyl carbon and nucleophiles reacting there, with or without the help of protonation. Okay. If this were an aldehyde ketone, the nucleophiles add, you're done. For carboxylic acids in the derivatives, a nucleophile adds, and then the X group often leaves. Okay, so you take one carboxylic acid and you make usually a new carboxylic acid derivative out of it. So they're interconverted in various ways. So in base, it's addition, elimination. That's easy. In acid, it's protonation, nucleophile, deprotonation, reprotonation, 2 steps, and then loss of the leaving group and deprotonation. So acid catalyzed mechanisms are always longer than base catalyzed mechanisms. But these are the core mechanisms for all carboxylic acid derivatives, but there are a lot of variations on these themes. Okay. This would be most generally applicable to hydrolysis of esters, where the nucleophile is water hydroxide. Okay. So we're going to see this played out in various ways with variations. And if you know the basic mechanism here and understand why some do it in slightly different ways, it'll be a lot easier to learn them all. Okay, so formation of acid chlorides were referred to before, and now it's part of this chapter. Thionyl chloride is a favored way of doing it. The same thionyl chloride you use to make alcohols, or chlorides out of secondary alcohols with retention. That strange reaction. Phosphorus trichloride, phosphorus pentachloride can all be used. I'm showing an actual reaction here at the bottom. The byproducts are HCl and SO2. Don't breathe it. It fumes noxious stuff when you do this. Okay, a mechanism for this is the thionyl chloride actually can activate the carbonyl through this type of a complex. Okay, so think of the sulfur oxygen double bond as kind of a carbonyl group. Addition, elimination of chloride gets you to this. And now the chloride that you've released can react here to give you this intermediate. And this intermediate can now immediately eject SO2 and chloride, 3 arrows at once, to give you the protonated product, and now just deprotonating with chloride. The reaction with thionyl chloride is usually run in thionyl chloride. Unless it's a solid, you often do this without a co-solvent. Okay, so this follows the basic muster I gave you, but thionyl chloride plays a unique role here. Okay? What time is it? About half done. Okay, esters are one of the most common carboxylic acid derivatives, and they can be made from acid chlorides. Okay, acid chlorides are the most reactive derivative we're going to see. They're so reactive that an alcohol doesn't need help. It can add to give this, and the chloride is immediately spit out. Okay, this carbon of the carbonyl group is more electropositive because of the electronegative, the chlorine, and that's what makes this possible. And so it's just addition, elimination, and then you got to do the deprotonation. You're making HCl, and sometimes you add triethylamine as a base to react with HCl. It's not absolutely necessary, but it's very common. It's more the rule than the exception. Which OH? Here? The OH? The H is lost as HCl. So the
No. I'm talking about the previous slide.
okay, that's what I was wondering. OH. Oh, my arrow's in the wrong place. Oh no. No, the arrow's right. This lone pair makes the double bond here and becomes the carbonyl group. This thing is swinging up top because this whole thing is leaving. Okay, so this oxygen is that oxygen. Okay? Yeah, I actually probably should point that out. Okay, so just a word here on mechanisms. We teach them as kind of a clean scrub, purified entity, and they're not that simple. Okay, this is the mechanism that starts out. But as this reaction goes, if you have no base there, you're getting HCl. And so at some point, some of the reaction may be acid catalyzed. Okay, I'm not going to worry about such subtleties, but I want you guys to have a better awareness of the complexities that go on. So mechanisms can change because the reaction conditions are changing, because you're generating HCl. Okay, so if I ask for a mechanism, you can absolutely ignore this. Okay, and if you actually showed me a mechanism catalyzed by HCl for this, I'd give you credit. Because at the end, hey, that works too. Okay. Anhydrides can be used to make esters. Anhydrides aren't used that often. What time is it? I think I'm about done. Anhydrides, you waste half of it. Half becomes the carboxylic acid, half becomes the ester. But acetic anhydride is universally used, okay? And here it's generally the anion that needs to add. So just a tiny trace of ethoxide will drive this. And it's the same mechanism, addition, elimination, you got your product and acetate. Okay, and that's just, these can be done without acid chloride, but usually aren't. And pyridine is used, and I'm going to show a mechanism for that some other time. Okay, I'm out of time. Thank you. I will stay for questions.
Thank you, Professor. Have a good day.
Sure, we about made it halfway. That's
Take care.
pretty good.
Take care, Professor.
Yeah, as I said, this chapter doesn't have a lot of new conceptual stuff that's really challenging, but there's a lot in the chapter. It's a different type of chapter.
Thank you, Professor.
Sure. Jack Riel, am I pronouncing that right?
Yeah.
Okay.
So my question is, you said that this mechanism can be done with tea, but are you showing this in this slide, or you just letting us know that it can be done with tea?
No, triethylamine, TEA. It's not tea.
Actually.
We never pronounce that word. It's cute.
But
It took me
you
a
just
second to
letting
know what
us
you
know.
meant. Yeah, TEA, triethylamine. It's like LAH. We don't call it LAH law.
But you just letting us know, like, oh, you can do this with this, but you're not
Actually,
actually showing in the slide.
You generally have either triethylamine or pyridine in here. The reaction's very slow without it.
Okay, thank you.
Okay, we're not that patient, but the pyridine changes the mechanism. We'll see that later. Jackie, what's your dog's name again?
This is Leo.
Leo, that's right, the lion.
Leo the lion. I just woke him up from a nap, so
Oh, poor thing.
I know.
Well, you know, if they have nothing better to do, they just lay down and take a nap. I wish I could sleep like a dog.
I know. Well, he and I went on a little expedition today because I had a long week. So I took the morning off from like all my responsibilities and I took him to Roosevelt Island.
Oh, really? Is there nice places to walk there?
Yeah, it's actually really nice.
There's a cable car over there, right? Is that the right one?
It's a tram, yeah.
A tram? Yeah, whatever you call it.
So I took him on the tram and there's a baseball field right by the tram and I just let him go off leash and he goes insane.
Yeah.
And then the ferry goes from there to Long Island City.
Okay.
And I took Leo to my parents in Long Island City to see my mom before she had to go to work.
Oh, I'm told Long Island City is an interesting area.
It's pretty hip now.
Yeah. Yeah, it's getting expensive.
Well, my parents are a little older and it wasn't that they couldn't keep working, it was the commute that was killing them.
Oh, yeah.
So
I hear you.
they're actually renting out their house and they rent in Long Island City. They don't
Okay. My daughter was an intern at the aquarium last summer. She got to work with the animals and she got trained to be what they call it, a host, a tour guide for the people visiting the aquarium, and the aquarium never opened.
Oh no.
So she was fully trained and never saw a customer.
Oh,
But she got to learn to work with the seals and the sea lions, and she loved it.
that's a really cool job.
Yeah, it was kind of an expensive thing. We had to rent an apartment for her because
Oh, yeah.
she doesn't have the driving experience to want to drive back and forth.
Right.
This
Well, and
summer-
driving in New York is hard.
Yeah, this summer she's got an internship. We think it's not approved yet. She has a good feeling. We got our fingers crossed, but it's with the what do you call it? I can't think of it. The cooperative, Cornell Cooperative.
Oh,
There's a place just north of us, so it's going to be an easy drive for her. So I'll be carless this summer. She'll be using my car.
oh, it's not at Cornell Tech. It's in
It's up in northern Rockland County. I don't know exactly where.
Cool.
Yeah, there's Cornell Cooperatives everywhere. But she'll be full-time there for whatever many weeks it is. Not being paid a lot, but being paid something.
Better than nothing.
Oh yeah, free internships, that's slavery. Shouldn't be allowed.
I did a lot of those.
Yeah, they shouldn't exist.
I think they abolished them after I graduated college, actually, my undergrad.
Okay, you wanted to talk when everyone else is gone, right?
Yeah, I did, but I'll just give people a chance to ask questions if they had.
Yeah,
any.
anybody if you don't have a question or if nobody asks a question soon, we'd ask that you log off because someone wanted to talk to me. Siring, did you need something? Is it private too? Yeah, text. I hate sending long text. I don't mind getting long texts. I talked about late submissions on the exams already. I have everybody's timestamp. And if somebody went 15, 20 minutes over, I am not going to worry about it. There was a lot of instability in Blackboard while a lot of the class was taking it. So I'm going to be especially accepting of late submissions. So you shouldn't have a problem. Yeah, I didn't know you guys went back and checked your first post at the time. I thought you'd write it down. My bad. Oh, let me turn off the recording.